This is a chapter on gravity. Gravity varies very, very slightly throughout the planet, depending on what the density is underneath it. Gravity travels in wave formation, and gravity creates these gravity wells. And in addition, gravity will actually bend light. All those things are fascinating, but what we're going to look at in this particular video is Kepler's laws and how they affect planetary motion. To do that, we have to go back in time to a little bit before Kepler and look at some major astronomers. We're going to start with Copernicus. Copernicus was Polish, he practiced medicine, and he was a canon in the Catholic Church. In his spare time, he did astronomy. He was a pretty serious kind of guy, and he did a lot of studying. He actually wrote a book on astronomy with his results, but he waited until he was dying before he published. Why wait until he was dying? Well, you got to realize what his results were. He basically showed that the motion of the planets is way easier to explain if we assume the planets revolve around the sun. Why is that a big deal? Well, you got to realize at the time there was a strong coalition between the church and the state. The church said, "We are the most important things around. God put us here and everything revolves around us." And the kings, that is the state, the kings said, "We have been appointed by God. We are the most important things around. And as all planets revolve around the earth, all of our subjects should revolve around us." So, if Copernicus published, he would get his king really mad at him. More critically, because Copernicus was a serious Catholic, if he published, he took a chance that the Pope would excommunicate him from the church. Excommunication to a Catholic means that he's going to spend a long time in a location that he really did not want to be at. So Copernicus trusted that he had good science, and he waited until he was dying. And Copernicus trusted God. He knew he'd recognize good science when he saw it. So he waited until the Pope would have no power over him and things would be fine. Well, after Copernicus came a guy by the name of Brahe, who was not a serious person like Copernicus. He was a Danish astronomer. He lived on an island. He lived there for 20 years and recorded the exact positions of the planets and the stars. You got to realize all this stuff was handwritten down. He had to wake people up in the middle of the night to write this stuff down, and they had to use, compasses, and it was a lot of work, and he really did a good job. How did he get a Danish island? Well, Brahe was walking down the beach one day when he saw the king's son, the Danish king's son, drowning in the ocean, and he rescued him. And the king said, "Oh, you saved my son. What can I do to repay you?" And Brahe said, "Well, why don't you make me the court astronomer and give me an island and a yearly income, and I'll sit there and record all this stuff for you." And so the king did. Now, TB was no fool. He knew he was getting his money from the king, and he didn't want to upset the king. He probably knew that Copernicus was right, but Brahe didn't want to say that. So instead, he said, well, the sun and the moon orbit the earth because we are the most important things around. Those other lesser planets, they can orbit the sun, but the sun orbits us. So it's kind of like this compromise position. This compromise position in terms of astronomy was nothing, but Brahe's data, big deal. Best data around. It's still used today, and other astronomers wanted to get their hands on it. TB wasn't cooperating, though. He wouldn't let it out. So the next guy was very tricky. His name was Kepler. Kepler said, "I want your data." TB said, "No way." So Kepler said, "How about you hire me?" So TB did. Brahe hired Kepler as an assistant. Strangely enough, only 1 year after he was hired, Brahe died under very mysterious circumstances. They were in another country. They were carrying the data in suitcases because it was all handwritten. Brahe died, and Kepler grabbed the data and ran. So he kind of inherited it. Now, depending on what website I go to, It says it was 30 years of data or 20 years of data, and I'm not sure which one it is, but I do know the data was really good. Kepler's took about 8 years to study it, and he came to the conclusion that Copernicus already had, that the sun was the center of our solar system. Furthermore, he said the sun exerted some strange and mysterious force on the planets, which of course caused them to rotate around them. He then took the data and, without a computer, spent 8 years analyzing just the data on Mars to come up with 3 laws to describe planetary motion. 1, planets move in ellipses, the sun at one focal point. 2, planets sweep out equal areas in equal times. And finally, 3, the period square is proportional to the radius cubed. These laws are not simple at first glance. Kepler's first law isn't obvious by looking at our solar system. In all honesty, despite junior high science books, the Earth comes very, very close to moving in a circle. But it's not really a circle. It's actually an ellipse. If this is the sun, which looks like it's at the center of it, there's actually another foci, not too far, just off to the side, that we revolve around. There's a certain eccentricity to our planets. We exaggerate it when we make drawings, so it looks more like this in our drawings. That's not really true. In actuality, it is more like that. But for sake of exaggeration, we'll go like this. So Kepler said that the sun is at one foci of the ellipse, and the other one is off in imaginary space. So they couldn't quite describe what was happening from TB's data with circles. But if they made things ellipses, the math worked out. Now again, it's not much of an ellipse, but it's there. Kepler's second law says that planets sweep out equal areas in equal times. So we're going to start sweeping here. If we look at this yellow area, it's a long, thin pie. But if we were to calculate the area, it would equal the area of this green, which is like a short piece of, but wide piece of pie. So all of these individual different colors all cover the same area. But if we look at the planet's speed, okay, it's going really fast down here. Over here, it goes really slow. Why is that? Well, consider conservation of energy. Right here, we've got a high potential energy because we've got a big distance from the sun. We have a high potential energy and a low kinetic energy. Here, some of the potential changes to kinetic. Here, some more changes. More. And we get down to here, and we're closer to the sun, so we have a lower potential energy. Our height away from the center is smaller. If we have a lower potential energy, conservation of energy tells us that it all had to be converted to kinetic, and so the planet's going much faster. Let's exaggerate that eccentricity even more so you can see it clearer. So we get close, the planet just swings past the sun really fast. Swing, gets out far away, it goes really slow. Fast, slow. Fast, slow. Again, it's a conservation of energy. High potential, low kinetic. Low kinetic, low speed. Over here, low potential, high kinetic. High kinetic means high speed. Let's take a look at Newtonian features that come from Kepler's laws. So when you throw Newton and Kepler together, we get some of this stuff. Some of this we already talked about. If we look at that blue vector, it's representing the velocity of the planet as it orbits. The velocity vector is small when it's far away and big when it's close. If we take a look at the force vector, we'll notice that the force is always pointed to the object that the planet is orbiting around. in this case, the sun. The force of a circle or an ellipse always points towards the center for a circle or one of the foci for an ellipse. So this force, created by gravity of course, always points towards the planet you're orbiting. Notice that the force is greatest as you get closer to the sun. And that makes sense. We know gravity depends upon distance, and so if our distance has gotten smaller and the mass has stayed the same, then of course the force of gravity has to be larger. So small force of gravity, big force of gravity. Small force of gravity, big force of gravity. Just like velocity. Kepler's third law, the period squared is proportional to the radius cubed, gives us this really neat math formula that we're going to have fun with later on. What do we mean by period? Period is the time it takes to complete one orbit. So the period of the Earth is 1 Earth year, the time it takes to go around the sun once. Radius is how far we are from the object that we're orbiting. And the interesting thing about this formula is you don't have to use metric units. It doesn't matter what units you use as long as they're consistent. The reason this is because this formula comes from a more basic truth that Kepler came up with. That basic truth is that the period squared divided by the radius cubed of any planet, that ratio is the same. So if we know the period of some planet, like the Earth, how long it takes for the Earth to go around the sun, and we know how far the Earth is from the sun, then as long as we know something about another planet, like how long it takes for, say, Jupiter to go around the sun, then we can figure out what its radius is, because this would be our unknown. So the fact that this period squared divided by radius cubed is a constant no matter what planet we're talking about is really a big deal. It allowed astronomers to come up with all kinds of new information about the other planets. Taking Kepler's third law, we combine it with Newton's law of universal gravitation, and we can come up with some variations of the third law. So let's take a look at Kepler's laws again. His first law, Kepler's first law, each planet's orbit about the sun is an ellipse. The sun's center is always located at one focus of the ellipse. Sun, planet. Now they're almost circles actually. We always exaggerate those ellipses. Kepler's second law. Kepler's second law, the imaginary line joining the planet and the sun sweeps equal areas of space during equal time intervals as the planet orbits. Area 1 in 5 days, Area 2 in 5 days, Area 1 equals Area 2. Kepler's third law, the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their ellipses. In other words, their radius. The farther away from the sun a planet is, the longer its orbital period, is another way of saying that.